Yeah, so I'm recording. Okay, welcome everyone. The second talk in the series, but the first, which is purely online. Thanks everyone for coming. Thanks especially to Jamie for coming to talk to us. Jamie's a postdoctoral fellow at the Black Hole Initiative at Harvard, and her research concerns the use of models and simulations in the detection of gravitational waves, mainly by LIGO and Virgo, and the epistemological consequences of this. And very suitably from what I've just said, today Jamie's going to be talking about epistemic circularity in the LIGO-Virgo observations of gravitational waves. And as you can see, the title of the talk is Black Hole, Coalescence, Observation and Model Validation. So I'll hand over to Jamie.
Great. Thank you so much for the introduction and for the invitation to speak. I hope everybody can hear me properly. Wave wildly if you can't. I understand that that is a very bad strategy for finding out if one cannot actually be heard. Okay, so yes, today I'm going to be talking about the LIGO-Virgo collaboration and their detection of gravitational waves, and then the use of those gravitational waves to observe black holes. And in particular about sort of the role that models and simulations play in the methodology of LIGO-Virgo and some sort of epistemic challenges that raises. So to start off with, I'm going to give you a very quick crash course in gravitational wave astrophysics. Please, there's going to be a fair bit of sort of technical details. I'm going to highlight what I think is actually important, so don't worry if things pass by, but if you need to clarify something as I'm going through, please feel free to raise hand or whatever, and I'll be happy to answer clarificatory questions as we go. So yeah, I'm going to start with the crash course in gravitational wave astrophysics. Then I'm going to talk specifically about a couple of aspects of the methodology that depend on having accurate models, both of binary black hole systems and the gravitational waves that they produce. And then I'm going to discuss what I see as a sort of epistemic circularity problem that arises as a result of this model dependence. Finally, if I have time, I'm going to talk a little bit about how, despite this circularity problem, the LIGO-Virgo collaboration does go about testing general relativity and sort of how we should understand these tests as a sort of response to the methodological challenges of the epistemic situation that they're in. So first, gravitational wave astrophysics. So gravitational wave astrophysics was sort of firmly launched by the first direct detection of gravitational waves in 2015. This first event, GW 150914, is pictured to the right. The top box is the top boxes are the measured signals from two interferometers. The sort of second row is the theoretical representation of that signal via numerical relativity simulations. And then finally, we have the sort of the residual noise after the signal has been extracted. So that's just a bit of a visual for you. What this really is that the LIGO-Virgo collaboration has detected gravitational waves, and this doubles as the first observation of a binary black hole merger, because these gravitational waves were produced by the sort of very fast orbits and eventual collision of two black holes. So in this sense, it's an observation of a binary black hole merger. So what is it they're detecting? Well, the Einstein Field Equations admit wave solutions. That's the gravitational waves. You can think of these as analogous to ripples on water, except that the ripples are on space-time itself. The slightly better, or technically better, analogy is probably with electromagnetic waves, although this is a bit less visually satisfying than the water metaphor. The effect of a passing gravitational wave can be seen in terms of its effect on a ring of test particles. So in this picture on the right, if you have a ring of test particles with no forces acting on them and a gravitational wave passes through, the effect is to squeeze and stretch, repeatedly squeeze and stretch the ring of test particles. And there's two polarizations, so that's why there's two images there. There's the plus and cross polarization, so one squeezes and stretches it up and down and left and right, and the other is on the diagonal. And any gravitational wave is going to be a combination of these two polarizations. So a combination of those two effects. Gravitational waves are detected using gravitational wave interferometers, which use this sort of ring of test particle idea. So here I have pictured two of the LIGO interferometers. They have this L-shaped configuration. And at the end of each of those arms is a mirror, which acts as a test particle, sort of part of this imaginary ring. And so when a gravitational wave passes through, it moves the test particles, and it in effect changes the length of the arms of each, changes the length of each arm of the interferometer relative to the other. And the interferometer is set up in such a way that it can detect these really tiny changes in the lengths of the arms. And so this fractional change in length is called the strain. And it's the strain that is actually measured by the interferometer. So here I just have a very tiny sample of the LIGO-Virgo data. And as it happens, this is data from around GW 150914. So there is a signal in this data in some sense. There's also a lot of noise because one of the great challenges of gravitational wave astrophysics is that of extracting a signal, the gravitational waveform, from very noisy data. This is just a visual representation of the noise in the interferometer as a function of frequency. And this is the measured noise over a period of time on average. Some of the noise sources include things like logging trucks nearby the interferometers. If there's a thunderstorm, it creates a lot of noise. There's sort of a million different things that can create noise in this interferometer because it's so sensitive. And so the interferometers are both physically isolated as much as possible from the system and extremely sensitive to gravitational wave signals to try and sort of get the ratio of the signal to the noise to be a little bit more optimal for extraction. Now, in gravitational wave astrophysics, there's sort of at least two initial observational goals. The first, of course, is the detection of gravitational waves. So the initial sort of goal for LIGO was to provide the first direct detection of gravitational waves. And that just means, showing that they really do exist. The second goal is the sort of more astrophysical goal, which is when you take the gravitational wave signals that you've observed and then use them to make inferences about the source systems that produce them. So for LIGO, this is typically binary black hole mergers. It can also be binary neutron star mergers or combinations of black holes and neutron stars. And so moving forward, it's that second goal that's really the sort of exciting astrophysical goal for sort of probing new physics and learning about the universe. And just to sort of prefigure what I'm going to say, both of these goals actually depend on having highly accurate models of plausible gravitational wave signals in advance. And especially in the second case, also models of the system that produce those gravitational wave signals. Okay, so I'm now just going to talk a little bit about the specific methods for achieving those two goals. So obviously the LIGO-Virgo methodology is very complicated. I'm going to focus on two particular parts of the process. First, what's called template matching. This is the way that they extract signals from noisy data, essentially by trying to find a match between the measured data and a template that's been worked on in advance. And then secondly, parameter estimation, which is the process by which you determine the properties of the source system that produced it. Okay, so detecting gravitational waves. The overall strain, that's S, measured by the interferometer, is just the sum of the signal that we're looking for, H, and a whole bunch of noise. And the noise is a big mess of things. There are two key types of searches done by the LIGO-Virgo collaboration. The first is a modeled search, and this involves a process called match filtering. Now, the basic idea behind this is to take the observed data, that's S, multiply it by a known signal, that's the signal you're looking for, H, do some fun integration, and this has the effect of sort of amplifying the signal that you've multiplied by. So if the signal H is there in the data, doing this process is going to amplify it such that you can observe it and extract it. If reading integrals at fast pace is not your thing, don't worry about it. All that you need to know is that this process requires knowing the signal in advance. So in order to do match filtering, you need to know H before you start. Now, of course, this is a problem for LIGO because you don't know what signal is going to be passing through your interferometer. You don't know when it's going to arrive, and you don't know the exact source system that's going to have produced it, so you don't know the exact form. So what you have to do is develop an entire library of plausible signals that you might expect to observe. For these experiments, that's a library of about 250,000 templates. So the data has to be searched using all of these templates. There's also this an unmodeled search. I'm not going to be talking too much about this because, but it's important to know that it does exist. So this just involves searching for sort of a spike in power in each of the interferometers, and specifically looking for spikes that match up across interferometers, because those are likely to be produced by actual signals rather than random noise. The unmodeled searches aren't as efficient as extracting signals as the modeled searches. So if you want to be doing sort of physics with your signal, or you want to be extracting the full signal and getting a high signal to noise ratio, the modeled searches are preferred. But of course, having the unmodeled search there does provide a nice check on the fact that the modeled search is doing more or less okay. Okay, so parameter estimation. This is the process by which you look at the gravitational wave signal and you try to work out what the source system was like, try to infer the properties of the source system. So the source systems for gravitational wave signals, such as binary black holes mergers, are characterized by 15 physical parameters. Some of these are intrinsic to the system, things like the black hole masses and spins. And some of them are just to do with our relationship to the source. So the distance to the source, the sort of inclination of the orbital plane relative to the line of sight. These are just to do with, the relation between the observer and the source system. And you also have to add 10 additional parameters per interferometer for calibration errors or calibration uncertainties. So all in all, a typical search, a typical parameter estimation process for 3 interferometers is dealing with 45 parameters, which is of course a challenging problem to do this all at once. The LIGO-Virgo collaboration does this using Bayesian methods. Specifically, they have this package called LAL inference that uses different Bayesian algorithms in order to sample this very large parameter space and give posterior distributions for all of these parameters. And you can see an example of that in the right-hand side. Now, importantly, these Bayesian methods rely on having, once again, accurate models worked out in advance. What these models have to do is the models themselves have to take source parameters and map them to gravitational wave signals. And if you have such a model, then you can use your Bayesian methods to go from the gravitational wave signal and work out what the most likely source parameter is. So the model goes from the parameters to the signal, and then you use Bayesian methods to go back from the signal to the parameters. Now, what are these models? Well, the first thing to note is that there are no exact analytical solutions to the Einstein Field Equations for systems like this. So straight away, you know that you've got no exact solutions, which means that you're going to have to be using a range of models and simulations, both to develop this library of templates I mentioned and to do parameter estimation. So I'm not going to go into much detail about these models, but I'll just sort of mention them quickly. So post-Newtonian approximation is the sort of familiar approximation scheme where you take a known Newtonian solution for a sort of given system, and then you add relativistic corrections. This works really well as long as your sources are not moving too fast and as long as the gravitational fields aren't too strong, because then the relativistic effects become very important. And so this diagram on the right sort of shows the domain of applicability for post-Newtonian theory, compactness being how close the objects are together, mass ratio being how different the two masses are. And so post-Newtonian is going to work really well for the stage of the binary black hole merger, the early stages of a binary black hole merger, where you have two objects that are far apart, orbiting one another, but not too fast. I'm not really going to talk about perturbation theory because that's a modeling approach that's really used for systems like if you had a supermassive black hole and then a tiny black hole rotating around it where the masses are really unequal. LIGO is not going to be sensitive to those kinds of systems. It's more sensitive to the closer mass ratio. In the red here, we have numerical relativity. This is really the gold standard for modeling binary black hole mergers, specifically because it's as close as you can get to an exact solution to the Einstein Field Equations. And as such, its domain of applicability extends to the late stages of a binary black hole merger and into what's called the dynamical strong field regime. So that means—
Sorry, Jamie, can I ask a simple-minded question? Could this be either binary supermassive black holes or binary normal-sized black holes? Or is it targeted at the kind of little ones?
So I think that my understanding is that LIGO-Virgo is not targeting supermassive black holes.
I mean, I guess it's so rare to have galaxies merging and this happening anyway.
Yeah, I think that LISA is maybe targeting this more. This is the space telescope.
Cool.
So yeah, my understanding is that this is mostly just going to be small to intermediate sized black holes. Although if you did have two sort of equal mass supermassive black holes, I mean, I think that this would probably be a—
Yeah, that's what I was thinking. It's quite interesting. I guess it depends whether supermassive black holes are all similar sizes. Maybe some of them could be much bigger than others.
Yeah, there's a pretty big range. Yeah, okay. So I've done post-Newtonian, talked about numerical relativity. The disadvantage of numerical relativity simulations is that they're extremely computationally expensive. So running these on supercomputers takes weeks to months for a single simulation. So you can imagine that if you need 250,000 templates, you're not going to be using numerical relativity simulations for the whole parameter space. It's also expensive to run them for a long time. So you don't want to be modeling in general the whole merger with numerical relativity simulations because, you know, basically the early stages it's not necessary to use numerical relativity for that. So the actual models that are, the effective one-body formalism. This is a quasi-analytic modeling approach that in principle spans the whole parameter space. It sort of builds on post-Newtonian approximations. And it's called effective one-body because it sort of starts from the idea of sort of translating a two-body problem into a one-body problem to get the conservative dynamics and then adding like radiation reaction stuff. But the most important thing to know about the effective one-body formalism is that, first of all, it's not computationally expensive to use. And second of all, it provides a tunable model that can sort of incorporate the results from other modeling approaches. And specifically, when it comes to the EOBNR modeling, essentially you have parameters that are representing higher post-Newtonian terms that are then tuned to the results of specific numerical relativity simulations. And then you can extrapolate to other parts of the parameter space where you don't have such simulations. So EOBNR is these tuned effective one-body models. And then the other sort of hybrid approach to modeling is called IMR phenom, or these are phenomenological models. And this basically involves taking post-Newtonian results and sort of gluing them on to numerical relativity simulations to get a full waveform. And then again, sort of extrapolating to different parts of the parameter space where you don't have numerical relativity models. So the EOBNR and the IMR phenom are both these sort of hybrid approaches that incorporate the results of different modeling approaches in order to generate the kind of models you need for the methods I just described. Okay, so here's, I think, an initial worry that I'm not going to spend too much time on. But when it comes to gravitational wave detection and the match filtering process that I described initially, there's a very sort of clear worry about the theory latentess of observation, or perhaps better, the model latentess of observation. So the template-based search methods mean you can only find specifically what you're looking for in the data. And so it's a fairly clear example of theory latentess of observation. Now, of course, I think while this is a very clear example, theory latentess of observation is a fairly generic worry about experiments. And whether or not it's generically worrying is, of course, highly contested. I'm not going to be addressing that sort of more general question here, but instead I want to think about 3 specific worries that you might have based on this sort of model dependence of specifically the detection of gravitational waves. So the first concern is the problem of false negatives. So if you don't have a template corresponding to it, you're going to miss signals in the data. The second is the problem of false positives. So if you're searching with all of these different templates through all of the data, it seems likely that sometimes noise is going to mimic one of your models, and you're going to think it's a gravitational wave and it's not. Now, I should say that number 2 is what the LIGO-Virgo collaboration was most worried about as they sort of prepared for detection of gravitational waves. And their methods are pretty carefully designed to avoid this. Most importantly, you need detections in multiple detectors at the same time in order for it to count. And if you do the statistics based on the noise based on the data over long periods of time and how likely these simultaneous triggers are, you can work out just how likely it is that you're going to get noise mimicking a signal in both detectors at once. And it's pretty unlikely, at least for strong signals. So that one's, I'm going to set aside. I'm pretty much just going to set that aside. I think the most concerning thing, especially once we start thinking of the sort of astrophysical goals of LIGO, is the question of imperfect signal extraction. So this is the case. So if you have imperfect models, you're going to extract the waveforms, and the extracted signal is not going to match the sort of true gravitational waveform that's passing by, or it's in some sense going to misrepresent it. So number 1, I think, is something you should be concerned about, but in the sense that, if we are missing signals, then that's a bad thing. We could be missing really interesting stuff. But here, you can sort of fall back on the unmodeled searches a little bit because they're not modeled. They're going to find signals perhaps less efficiently than the modeled searches, but they're more likely to be able to pick up on signals that don't match your templates. think the most worrying one is number 3. So here, once again, fully extracting sort of an accurate representation of the physical gravitational waves is going to depend on having accurate models of the gravitational waveforms based on these 2 sort of hybrid modeling approaches I mentioned. Okay, so I think the more interesting worry comes from, I've called it theory latentness. It's really more like model dependence of the observation of binary black hole mergers. So when I described the parameter estimation process, I emphasized that any inferences about the nature of the source system are based on models such as these EOBNR and IMR phenom models. And as a reminder, these models map sort of source parameters to gravitational waveforms. And any inferences we want to make about the source system is going to have to be, using those in reverse. So just some sort of further things to sort of compound the problem, I suppose. First of all, we're dealing with astrophysics. So the source systems in question are not things that we can manipulate or intervene on. And because they're binary black hole mergers, they don't emit electromagnetic radiation. So we have no independent empirical access to these target systems. And what's worse, these mergers are occurring in previously unobserved physical regimes. These are sort of the extreme physical regimes for our theories of gravity and space-time, general relativity. And so if things are going to break, if the theory is going to break down, if our theory no longer provides accurate descriptions in some regimes, this is where it's going to happen. Okay, so, and sort of the worry is that because the observations are model dependent, there's a real risk that any such deviations from DR are potentially going to be masked by the methodology. So a lot of this then comes down to a question about how do we know that we actually have good models of these source systems? If we're basing all of our observations and inferences on these models, we certainly want to be concerned about the justification for trusting them. And in particular, how good are these models within the dynamical strong field regime? That is that sort of final stage of a binary black hole merger where things could potentially be breaking down. I'm going to follow actually a couple of physicists, Yunus and Pretorius. Pretorius is one of the first people to successfully do a numerical relativity simulation. And sort of describing these in terms of what they call modeling bias versus theoretical bias. So the first being modeling bias being inaccuracy of the models relative to the theory. So if our models are sort of not accurately representing the predictions of general relativity for a given source system, this is a source of modeling bias. And then there's this worry about the inaccuracy of general relativity for describing the source system at all within these regimes. So if the predictions of general relativity do not provide an accurate description of these systems, that's going to be a source of theoretical bias, using their terminology. Okay, so how do we know that these are good models, if indeed we do? As I mentioned before, there's no analytic solutions to compare them to, so we can't use analytic solutions, even for simplified systems as benchmarks. I mean, actually, these are, in some sense, very simple systems. These are two-body systems. Even for that, there's no analytic solutions. One argument comes from robustness. So it's common to compare the different modeling approaches and their results for, especially for particular systems. This paper I cite here does so for GW 150914, that first detection. And because these are different modeling approaches, the argument is that the agreement in their predictions gives us reason to have confidence in the modeling approaches themselves. Now, from what I've already told you about these modeling approaches, you should perhaps be a little bit skeptical about this, not in that it's wrong, but in that it's fairly limited. Because these two modeling approaches are incorporating very much the same ingredients. They're both going to be based on numerical relativity simulations, post-Newtonian results. So, you know, it's perhaps not entirely surprising that they would agree, is the point. In the end, a lot of the confidence in these models comes down to confidence in the ingredients, both here, post-Newtonian approximation within the early stages. I mean, we have observations of systems, of binary systems outside the dynamical strong field regime where post-Newtonian approximation works well. Hulse-Taylor pulsars, for example. And most importantly, confidence in numerical relativity within the dynamical strong field regime. I cannot say that today. So effectively, the numerical relativity simulations are acting as benchmarks in the absence of analytic solutions. They're essentially providing much of the justification for confidence in the models that are actually used. Even though, note, we have only a few numerical simulations, they don't span the parameter space, and at least at the time of GW 1509-14, they didn't incorporate all of the physical effects that we know to be important. So early simulations didn't incorporate things like precession. Okay, so why do we think that numerical relativity simulations are reliable, and particularly reliable for these kinds of systems? So I'll talk about this sort of in terms of the verification and validation. So verification being roughly whether or not a simulation is accurately solving the equations it says it is. We can think of this as being to do with the modeling bias, unison Pretorius we're talking about. Basically, this is accuracy relative to the theory in question. So how do you test that simulations are actually getting the predictions of GR right? Part of this is code verification. So this is the stuff that practitioners actually do in terms of being confident that their code is doing what they think it's doing, that the different modeling decisions that they're making are going to lead them to effectively solve the equations. I'm not really going to talk about that because it's both very complicated and none of you are numerical relativists, I would assume. So yeah, it's essentially, I think it's going to take a numerical relativist to describe this with any accuracy. Solution verification involves looking at the actual solutions that are being spat out of these simulations in order to try and determine whether they're right. So things like convergence studies, where you increase the resolution of the simulation and make sure that it's not changing as you increase the resolution. And then interestingly, we come again to robustness arguments. So actually, robustness arguments are playing a role at pretty much every stage of the justification of numerical relativity simulations, including for a lot of the issues that come up in code verification. But sort of on the most zoomed out level, you get a lot of comparisons across different simulation approaches. So there's a lot of different choices you can make in setting up your simulation. But if you take the same source parameters, you should be getting the same results out. And so here I've cited a couple of papers where they're doing these comparisons between simulations and finding really impressive agreement between them. But yeah, I think it's probably worth emphasizing that in the absence of analytic solutions to compare it to, a lot of this does come down to robustness arguments at various stages in the process. Now, validation, this second part of the verification and validation framework, this concerns roughly the accuracy of the simulation outputs relative to the real world. So this is where you're actually comparing your results to the actual state of the source system. And this is the stage where you're trying to counteract what Unison Pretorius called theoretical bias. So inaccuracies with respect to, inaccuracies of general relativity in actually describing the systems of interest. So because the LIGO-Virgo collaboration are observing systems in regimes that have never been observed before, the LIGO-Virgo observations are in fact the only observations that are really relevant for validating numerical relativity simulations within those regimes, which maybe should spark some little flags of concern, because I've just told you about how the LIGO-Virgo observations are dependent on having accurate models. And now I'm saying that confidence in these models as accurate relative to the source system, if you want to sort of validate these models, it's going to depend on the very observations that I just told you were model dependent. So here there's a circularity, an epistemic circularity problem that arises. So observations of binary black hole mergers are presupposing the accuracy of the models using in these observations, specifically EOBNR, IMR phenom, and the accuracy of those very models in the dynamical strong field regime, again, presupposes the accuracy of the LIGO-Virgo observations. So we have the circularity problem, where the justification of one depends on the other. Whole bunch of text on this, but the take-home message from this is that this is coming from practitioners. Again, this is the Unison Pretorius numerical relativists, and they give an example. They give several examples. This is one of them, of the ways that these presuppositions could be sort of disguised in the LIGO-Virgo methodology. So in this example, we have the first bold section is describing a sort of modification of general relativity that could come into play in these source systems. And the second bold is telling us how such a deviation from GR could not only be disguised by the LIGO-Virgo methodology, but lead us to sort of systematically biased inferences about the kinds of source systems we're observing. In this case, I think the example is that we would systematically underestimate the black hole spins. And yeah, this is just a nice example. If you've got models, if you're using general relativity models, but it turns out GR is not the correct theory for these regimes, this is going to lead you to be systematically misled about the inferences you make. Okay, so taking stock. It's worth pointing out, gravitational wave astrophysics is in its infancy relative to electromagnetic astrophysics. Gravitational waves are basically just really hard to detect. That's why it took 100 years from their first prediction to actually measure them. And these detectors are very new. So I haven't really talked about this side of things too much in this talk, but suffice to say that just sort of the on-the-ground physical detection is really challenging. We also have this epistemic circularity problem I've been talking about, because gravitational wave astrophysics is probing these new physical regimes where current physics may break down. And the methodology of gravitational wave astrophysics relies on having accurate models for target systems in these regimes. So we have methods that are dependent on models, but we're also looking at regimes where the models might break down. Model validation is going to be difficult because we can't directly compare to either analytic solutions or the target systems by any other independent means. And, you know, model dependence is a fairly generic feature of experiments, but there's some features of this situation that make it especially challenging. Namely, like this is astrophysics. So as with other observational or historical sciences, it's not possible to manipulate or control the target systems. And there's no independent access to the target systems. So if we're dealing with binary black holes, at least, no electromagnetic signals to compare to and sort of have some kind of consilience or coherence test. Okay, so I think I've got about 5 minutes left, if that's right. Okay, so to not leave on a very pessimistic note, because what I've just done is describe some of the challenges of the epistemic situation of gravitational wave astrophysics. I want to spend the last 5 minutes sort of talking about ways that especially the scientists are really going about overcoming these challenges and how we should understand these sort of with how we can better understand what they're doing now in with the context of understanding these sort of methodological circularity problems that have arisen. Okay, so the first bullet point, there are currently 3 interferometers active in the gravitational wave observation network. Adding new ones improves the data. It helps break some of the degeneracies that occur between parameters and helps improve the situation. Ask me in the Q&A if you want to hear more. Improving models and simulations is a very active area of research. And sort of the flip side, I guess, of the circularity problem and the model dependence is that you can really improve your observations simply by improving your confidence in your models. So incorporating new physical effects in your models means that you're going to be able to do much more with the same data. Now, another method that you might want to use in order to sort of break this circularity or deal with this problem is developing models for alternatives to general relativity. Unfortunately, this is really hard. Pretorius is currently trying to work on simulations to do this, but it's, you know, doing it for GR was hard enough. This is not looking like a path forward, at least for the near future. The other thing that might, it's sort of a surprising thing that you can do is actually testing general relativity with the LIGO-Virgo observations. Given what I've just said, this might sound like it would be impossible. But interestingly, I think that they're doing some interesting things. Just use interesting twice, but never mind. That are actually helping them overcome the circularity problem and at least looking for ways that their methods could be leading them astray. So in a few minutes, I'm just going to very quickly mention some of these tests. So they're doing a lot of different sort of, quote, tests of GR. I'm going to really just talk about a couple of them, particularly the residuals test and the consistency of the low and high frequency parts of the signal, just as a sort of illustration of the general point I want to make. So the residuals test, let me just take a step back. So when you extract a gravitational wave signal, you subtract the signal from the data. What you're left with is a bunch of, hopefully, just noise. The residuals test looks at the residuals, looks at what's left over, and sees statistically whether it's more likely to be noise or whether there's some indication that there's a signal left over. So first step is extracting the signal from the data. Second, the residual is then compared to normal detector noise where you don't think there's a signal. And so they do this test as a way of basically estimating how well they're extracting signals, how successful they are in extracting the whole signal and nothing but the signal. Now, this helps constrain violations of GR in the sense that your models are based on GR. And so if you're leaving things behind, it would be an indication that GR models were not working. And so perhaps there were deviations from GR. present. It's limited in the sense that there are degeneracies between parameters. So it is possible that you could successfully extract a gravitational wave signal with a GR template associated with a different set of parameters than that were those of the source system. So you could have two sets of source systems that actually map to the same or close enough to the same gravitational wave signal. And in that case, you're not going to be able to distinguish. You're not going to be able to spot the fact that something's gone wrong because, yeah, there is this degeneracy there. So it's not a strong test of GR, but it's certainly an important part of an overall sort of approach to testing the theory. And the second test I'm just going to mention quickly because I think it combines with the residuals test in an interesting way. So if we're confident that we've extracted the signal properly, then we can go on and do this low high frequency test, which involves breaking the signal in two. So you take the low frequency or early part of the signal, and you take the late or high frequency part of the signal, separate them out, and perform parameter estimation separately on each of those two parts of the signals. So the idea is that the early part, you are pretty confident that GR is correct. So parameter estimation can be considered pretty trustworthy. Subsequently, you do parameter estimation on the sort of more dodgy part of the signal where you think GR might break down. And then using sort of numerical relativity to sort of bridge the gap between these two things, you can compare the parameter estimation and see whether they're consistent with one another. Now, effectively, this is checking to see whether something crazy is going on in the second part. Because if there were deviations from general relativity in the high frequency or late merger part of the signal, this could then show up in having very different parameter estimation for the two different parts of the signal when you do them separately. And so I think this is a really interesting case in that it's a consistency test, but it's also managing to nonetheless, despite presupposing general relativity at each stage in this process, you're nonetheless able to sort of look for a way that those presuppositions might be leading you astray. Okay, I've just mentioned here Lydia Patton's work on the phenomenological deviations test, which I'm going to skip over now because I'm over time. But this is another really interesting way that they sort of managed to expand the ability to test GR without actually having to have alternative models to compare to. Okay. So some concluding remarks. Just to begin with, I think gravitational wave astrophysics combines sort of the epistemic challenges of both observational or historical sciences with some of those from fundamental physics. So on the one hand, remote, non-manipulable target systems, lack of sort of controllable experiments. You're sort of left at the mercy of what the universe provides. And on the other hand, the fact that we're probing these novel physical regimes where theory can be expected, or new physics is possible, and theory is not necessarily to be trusted. And so this makes it, I think, an interesting case in frontier science. Just by way of quick summary, I said that the detection of gravitational waves and the observation of binary black hole mergers, these depend in various ways on having accurate models, both of the properties of the source system and its dynamics, and also on the resulting gravitational waves. Oops. These models are effectively mediating between the high-level theory and the data. But this model dependence leads to a kind of circularity problem. It's an epistemic problem in terms of the justification. So the observations, the LIGO-Virgo observations depend on having accurate models of these systems, but the way that you go about validating those models ultimately seems to depend on those very same observations. thus the circularity. And at the end, I briefly mentioned that some of these tests that LIGO and Virgo are doing. And I think that these tests work together in interesting ways. So I gave the example of the Residuals Test and the high-low frequency test. Sort of put together, these are providing constraints on things that could be going wrong in the methodology of LIGO. Ways that the methodology could be masking deviations from general relativity. And so I think that these are best understood as a kind of response to the circularity problem inherent in the epistemic situation of gravitational wave astrophysics. And they can kind of be thought of as a sort of methodological bootstrapping, where you're testing different parts of what's going on in order to sort of bootstrap your way up to sort of testing whether GR is correct. Thanks. All that I've got left is a bunch of references. So.
Thanks so much for that really interesting talk. If we can all join in giving Jamie a quick round of applause, and then we'll take a 5-minute break, maybe just to ease, we'll just go until past. Or is that too long for people?
Sounds good.
Okay, cool. So we'll regroup at past.
And first questions from the students.
Oh yeah, sorry, I should have said, yeah.
So if you're a student